So welcome everyone. Good morning. It's good to be with all of you once again, talking about infinite series. I think that I think there's many topics that are my favorite topic, but I think this is another one of my favorite topics because there's parts of it that are really straightforward. There's parts of it that are surprising. There's interesting connections to other places in math. There's places where you can look and see that the great mathematicians were out to lunch, and it's always fun to realize that the people that are way smarter than us struggled with things, and that always kind of makes me feel good. Some of the pictures are cool, so lots of good stuff here. When we were together yesterday, we were mostly talking about geometric series, and then I think we ended talking about the telescoping series and the harmonic series. And we were sort of forming this list of various tools that we can use to investigate infinite series. Today, we're going to look at two more of those tools. We're going to look at the integral test and also the test for divergence. But before we do that, let's go through a few announcements. So today, we're going to talk about the test for divergence and also the integral test. Along with this, we get something called the p-series, and we get a little bit of error bound. So there's some extra stuff in here. This is what we're doing today tends to be relatively easy to understand, but not very powerful. Let me see if I can share what I always think of as a helpful chart. So there's easy, hard, weak, powerful. And we could maybe have other boxes as well. But what we're going to do today tends to be easy and weak. So we're going to do some stuff that's easy and weak. We are going to pick up one thing, which is the p-series, and the p-series is easy and powerful. So that's going to be a direct result. But as we're kind of going through all these items and we're formulating the list, maybe think about this basic chart and go, is this easy? Is this hard? Is it weak? Is it powerful? You only want to do hard stuff if it's powerful. Oh, wait, sorry, today. Yeah, today is here and it's here. It's actually in both places. So this is a terrible box. Something that's hard and gets you nothing out. That's the worst. The best is easy and powerful. Doing hard and powerful, that can be good, but it's still hard. So anyway, little box to try to help you understand how to prioritize items on the list. So without further ado, let's dive into our lesson. Okay. So we are beginning section 10.4 on the integral test and also the test for divergence. And so I'm going to begin by giving you this picture of the integral test. And so there's sort of two cases here. So what I want to comment on is that the definite integral, actually it's not a definite integral, it's this is an improper integral. Well, it would be improper if it had an infinity in it, because there's an n, depending on how you want to think about it. And okay, when I was learning cursive in 3rd grade, I did not think I would be needing it on the internet to teach in the middle of a pandemic. But this improper integral, usually we're going to have an infinity up here when this actually all works through. this improper integral represents some area under the curve. And what I want to point out is that the series is made up of a whole bunch of rectangles, and all those rectangles live underneath the gray area, you know, this shaded region. And so we can say that the series, whatever the number is that comes out from all the rectangular boxes, is less than the number that comes out of the integral. I think there's one thing that might be a little bit mysterious. What's the width of each one of these rectangles?
dx, dn, d.
Don't overthink. Do subtraction.
B minus A over N.
Don't overthink. What is it?
N minus 1.
No, I'm looking for some
electromagnetic field.
1.
Oh,
How about dx?
oh, N minus 1.
1.
What was that, Titus?
1.
It's 1. Right? Here we're at 2. Here we're at 1. Here we're at 3. Here we're at 2. Here we're at 4. Here we're at 3. So the width of each of those rectangles is just 1. So that's why so the height of this very first rectangle would be A2. That's the way they've described it. And the width is 1. So the height times the width would be the same thing as the height, even though the units are different. So that's why we can have here, it's like we have a delta x equals 1, so to speak. Make sense? Is there any questions about the connection between the sum of the rectangles and this series and the integral and the area under the curve? All right, so here's the main point. If this thing right here converges, I can't do V's. What does converge mean?
Approaches a number.
Approaches a number. So if this integral right here is a number, then the thing underneath it is also a number. That's the main point. If we scroll down and we go the other direction and we say that the area under the curve diverges, so if this one diverges, I can't do it. So this guy diverges. Diverges in this case means like is infinite. Then that means that the sum of the rectangles over here on the right is bigger, and it must also diverge. Okay. So what we've done is we've created a connection between integrals on the left and summations on the right. Does that connection make sense to everyone? Very good. All right, so here's the integral test. So the integrals test says, suppose that f is continuous, positive, and decreasing on 1 to infinity, and let a of n equal f of n. Then the series from n equals 1 to infinity of an is convergent if and only if the improper integral from 1 to infinity of f of x dx is convergent. In other words, if the integral converges, then the series converges. If the integral diverges, then the series diverges. This next note here is pretty important. Okay, so we should not infer from the integral test that the sum of the series is equal to the value of the integral. In fact, the sum of the 1 over n squareds is pi squared over 6, whereas the integral from 1 to infinity of 1 over x squared is just 1. So the thing is that the test, it tells you whether something converges or diverges. If it converges, then you still have to figure out what number it equals. The nice part about the geometric series that we played with yesterday is that with the geometric series, you actually have a formula that you not only know it converges, but you also know the value. And so that's kind of a powerful test or method in that sense, because it answers both of these questions. But knowing it converges tells you that it equals a number, you just don't know what the number is. Questions about that?
Is that why we would call it weak, because we're not getting that value that we want?
No, good question. So why weak? The reason I would call it weak is because this particular test is only as valuable as your ability to integrate. So I don't know about you, but I think that integration is super hard. Like, it's hard and it's long and it doesn't always work. Right? And so I would say that this test is weak because it's dependent upon something that's hard, long, and doesn't always work. And I would prefer to not be dependent upon things that might not always work. And I'd also rather, if I'm trying to figure out if an infinite series converges or diverges, I'd rather not be stuck with dealing with things like partial fractions and trig substitutions and strange integration techniques. So does that answer the question?
Yes.
Cool. Good question. Any other questions before we go on? Very good. All right. So this next note is not hard, but is important. So when we use the integral test, it's not necessary to start the series or the integral at n equals 1. For instance, in testing the series here, notice we're starting at n equals 4. So you see the n equals 4 there. And over here, we would start with the lower bound of 4 as well. So they are going to match, but they don't have to be a 1. It's not necessary that f always be decreasing either. What's important is that f be ultimately decreasing. And so, for example, you could have a function that did something along those lines. And you'd have the dots along it would be, here. So here, the green these are your ANs, and then the red would be your F. And so you notice that when we can even allow it to be negative, right? This would be okay. Okay, it can be negative, that's fine. It can be increasing for a while, that's fine. But what's important is that after some point, and usually this gets referred to like as a big N. Big N. So after big N, the function is always positive, it's always decreasing, and basically you run your integral test from whatever that point is forward. Yes. So that is, as long as the sum from little n equals big N to an is convergent, so is the sequence from n equals 1 to infinity. Because this is the early stuff would be a finite sum, and we know that that will converge. Question about this note or either of these notes? Very good. All right. Let's look back at an example that we worked on yesterday, namely the harmonic series. So when we were together yesterday, we started playing with the harmonic series. Maybe without looking at your notes, do you remember what that is? What's the harmonic series?
1 over n.
1 over n, and so that would, the 1 over n would give me the harmonic sequence. So if I want the harmonic series, I would need to do what?
The sum of 1 over n.
Yeah, sum of 1 over n from
Goes
n
1
equals
to infinity.
1 to infinity. So this is 1 plus a half plus a third plus da 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 da. Okay. So if we want to test this for convergence or divergence, so we would say, does it converge or diverge? Okay. We can use our integral test. So we could consider the integral from 1 to infinity of 1 over x dx. Which kind of integral is this?
So logarithm.
Improper. An improper one.
It's improper. It's not very British. It's an improper integral. So that not British improper integral would has an infinity in the upper bound. That's not cool. So as you may recall, what we do in that case is we set up a limit as t goes to infinity of the integral from 1 to t of 1 over x dx. I think in some of the homework, they used an a here instead of a t. Same thing, just whatever letter makes you feel good. Preferably not the letter O. Using O is a bad idea. So anyway, we evaluate the limit, or the integral. So we get ln of t going from 1, ln of x, wow dust, ln of x evaluated from 1 to t, which would be the limit as t goes to infinity of the ln of t minus the ln of 1. And what happens to the ln of t as t goes to infinity?
Infinity.
Goes to infinity. So we would say that this integral, what does the integral do?
Diverges.
Diverges. Okay. Yay. So we've done the hard work. Now we have to do one important step. We need to state our conclusion. So our conclusion here is that since the integral from 1 to infinity of 1 over x dx diverges, the harmonic series from n equals 1 to infinity of 1 over n also diverges. And how do I know it diverges? What's the test that we did?
The integral test.
Yeah, by the integral test. So this this justification at the end ends up being a kind of a, not difficult, but a big deal in this section. Questions about this example? Very good. So notice that we just proved once again that the harmonic series diverges. We didn't do this because we were uncertain as to the result. We proved that it diverged yesterday. But we did it using the integral test because it gives us a second way of understanding why it diverges, and also lets us compare two different techniques. The technique yesterday focused in on the partial sums and inequalities. This technique focused in on the integral test. So it's kind of a nice compare contrast of ideas. Also, the fact that we did 2 examples around the harmonic series is a reminder that it's really important. Not hard, but really important. All right. So let's go back to our notes for a moment, and let's start by updating the list. Let me say that again, the list. So we already had the geometric series converges when the absolute value of r is less than 1. We learned again that the harmonic series diverges. At the end of class yesterday, we introduced this idea of a telescoping series. And then right here in this section, we've introduced a new test called the integral test. And basically what we're saying is that the integral and the summation share the same fate. Share fate. For lack, some of you were on the line at the beginning of class and we were talking about Boeing, the airplane manufacturer, and how in some ways Boeing is a really good employer. They pay well, they have good benefits, there's a good retirement, there's all those kinds of things. And when planes are soaring, when Boeing jobs are plentiful, sharing the same fate as Boeing is a good thing. But when planes are crashing, for lack of a better way of saying it, when travel is grounded because of a pandemic, then sharing the same fate as Boeing is a little bit more troublesome, and certainly is troubling and a challenge for many people, even some of our classmates. And so that's a kind of a practical example. But here with the integral test, what we're saying is that the integral and the summation, the infinite series, share the same fate. This is nice. It's easy to understand. The catch is that it's weak because it's only as powerful, it's only as good as your ability to integrate. And integration is hard. And it doesn't always work. So the next theorem is a simple one. It says, if the series is convergent, then the limit of the terms goes to 0. If the series is convergent, then the limit goes to 0. Let me show an animation to help you visualize what this is saying. Okay. There's this S1, S2, S3, S4. Can you remind me what do these mean? So what does S4 represent here?
A partial sum?
Yeah, specifically which one?
The fourth partial sum?
Yeah, so that would be like A1 plus A2 plus A3 plus A4, right? Fourth partial sum. So we have our partial sums, and notice that our partial sums are approaching some limit s. And so the limit of the partial sums is s. That's great. And so now let's look at the terms themselves. In order for the partial sum, in order for the infinite series to converge, the terms themselves now have to approach 0. So if the terms don't approach 0, then we're going to always be getting jumps in the series. So if the series converges, that's telling you that the limit of the partial sums is equal to a number. So these are kind of saying the same thing. And that tells you that the individual terms, these guys up here, must go to 0. Questions about that? So thinking back to what we were talking about earlier with things that are easy and hard, powerful and weak, relatively speaking, evaluating limits is easy, but this is kind of a useless statement. Like, this theorem is not very helpful to you. Okay, so this is not a helpful theorem in general, at least the way it's written. And the reason is because the question that you're trying to work on is you're trying to figure out whether some series converges or diverges. Like, that's what you're trying to figure out. And this says, if you already know it converges, then the limit of the terms goes to 0. Well, if I already knew if it converged, I'd be done with the question already. Like, so who gives a darn? So this isn't a terribly helpful statement to us. So, and the catch is this note 2. So the converse is not true in general. If the limit as n goes to infinity equals 0, we can not conclude that the sum is convergent. And this is where the harmonic series ends up being a big deal. Does this series converge or diverge?
Diverge.
It diverges. Thank you. And how about the limit as n goes to infinity of 1 over n?
Go to 0.
It goes to 0. It's like unhappy 0. So the limit goes to 0 and it diverges. So just knowing that the limit goes to 0 is not going to help us. So close, but so far. Okay. Good news is coming. So the test for divergence. So the test for divergence looks at this thing the other way. It says that if the limit does not exist, or if the limit does not equal 0, then the series is divergent. So let me see if I can put it in context. So if we said that the limit of the terms equals 0, this gives us is no help. It's useless. But if we know that the limit, oops, sorry, let me write that again on white, sorry. Limit as n goes to infinity of an doesn't equal 0, then that tells you that it diverges. Okay. In my little chart where I have easy, hard, weak, and powerful, This particular one falls in the easy and weak category. It will rarely work for you. So this is rarely going to work, but it's super easy to do. And so when it does work, it's like, I don't know, it's like finding a $5 bill on the side of the road. You're like, wow, that was nice. Super convenient, barely an inconvenience. Super easy, barely an inconvenience. Okay, so let's see how this all plays out with an example. So in example 2, we have the sum, well, I'm going slowly today, sorry. Sum from n equals 1 to infinity of negative n over 2n plus 5. And we can look at the limit as n goes to infinity of negative n over 2n plus 5. And what's that limit equal to? Or more importantly, what is this limit not equal to?
0.
It is not 0. It's pretty close to a negative half, actually. And so since it's not equal to 0, what does that tell us?
Divergence.
Tells us that negative n over 2n plus 5 diverges by, what's the test we used?
Divergence.
The test for divergence. Thank you. This technique will rarely work, but when it does, it's, you know, just 1 or 2 lines. It tends to go really fast. Its limits are much easier to evaluate than integrals, and so we tend to be happy about it. So what does that mean? It means we've got something else that we can add to our list. So we had our geometric series, our harmonic series, our telescoping series, the integral test, and now we have the test for divergence. Test for divergence, again, easy, not very powerful, but easy. So let's move on and pick up one more thing in this section. So a simple but powerful application of the integral test is what we call the p-series. And this will be a powerful tool for us in the next section when we start talking about comparison tests. So p-series are of the form series from n equals 1 to infinity of 1 over n to the p. I think in this case you say, well, why p? I think this is p for power. I think that's what the p is a reference to. So the power's kind of like a power series. So in which p is a fixed number. So the n is changing, the exponent is fixed. Short version is that this is going to converge if p is bigger than 1. It's going to diverge if p is less than or equal to 1. And we'll show an example of that. In a couple minutes. So let's do a couple of p-series examples. Here I have C or D, converge or diverge. That's the question we're working on. So we could write this series as 6 times the series from n equals 1 to infinity of 1 over n to the 5th. And we do a careful analysis of it, and we see that, gee, this thing is a p-series. What is our p?
It's 5.
5, happy 5. So what does that tell us? Does it converge or diverge?
Converges.
Say again?
It's convergent.
Converges. So the series, hence the series converges because it's a p-series. Now you might say, well, great, Dust. You know, you're just telling us to take your word for it. Why would you know that? Well, we could prove it using the integral test, and the whole p-series comes out of the integral test. And so imagine that we looked at the integral from 1 to infinity of 6 over x to the 5th dx. This is again an improper integral. So we need to look at the limit as t goes to infinity of the integral from 1 to t 6 over x to the 5th dx. Antiderivative of 6 over x to the 5th, negative 6 over 4 x to the negative 4th. So it looks like we have negative 6 over 4 t to the 4th plus 6 over 4. This first term, what approaches what?
0? Or...
Yeah, 0. So this thing equals 6 over 4. So what? Like, what does this tell me? Why did we do all that?
To prove that it converges
By what?
using the integral test.
Therefore, the series of 6 over n to the 5th from n equals 1 to infinity converges by the integral test. Okay, so the p series is coming out of the integral test. It's just sort of a generalization of what we just showed. And if you compare the two strategies, notice that when we use the p series directly, we're just like, we know the answer to the question, no work required, just write down the answer. When we use the integral test, it required limits and integration, and it wasn't hard, but it definitely was a lot more writing. So this is a good example of why we like the p series. You know, we would prefer identifying something as a p series than using the integrals test from scratch. So one bit of clarification about this, notice that we ended up with that 6/4. So we have this sum 6 over n to the 5th, and we had this integral, and we found that this was equal to 6 over 4, or 3/2. So the question is, what does this thing up here equal?
Six pi over 4.
6 pi. Wow. Let's I don't know the answer actually. Let's do what every good mathematician does in 2020. Let's ask Wolfram Alpha.
How did you know?
Let's see. So series of 6 over n to the 5th equals 1. Let's see if this works. Yep, I don't know if you can see that. If that's clear. I think this is the Greek letter xi. It's like xi, but I'm not positive. Some funky Greek letter. And this is a good example of Wolfram Alpha not being terribly helpful to you. But the decimal approximation is this ugly number right here, 6.22 something, right, like that. And most importantly, it's very much not 6/4. It's not 6/4, right? So the key is that the integral zeta, I think you might be right, Nathan, thank you for that. We'll look up our Greek letters later, I appreciate that. So the point is that the integral test tells you what tells you whether it converges or diverges, but it doesn't tell you the number to which your series is converging. Does that distinction make sense? Again, we've got the question of does it converge or diverge, and then there's the second question of what number. And we were able to answer the converge part, but we're not really that much closer to the what number part at this stage. Questions or keep going? I think you're right, it is zeta, by the way. I looked that up. Very good. Yeah. Thank you, moderator. All right, let's do one more example here. So we have example, I think this is 3C. I got a little excited with my sigmas. Example 3C, so this is the sum from n equals 1 to infinity of 10 over the 5th root of n. And I want to know again whether it's C or D, converge or diverge. And so we could write this as the sum from n equals 1 to infinity of 10 over n to which power?
1/5.
1/5. So is it going to converge or diverge?
Diverge.
Diverge. 1/5 is very much less than or equal to 1. So this diverges by the p-series. It's not really a p-series test, but sometimes it can be, we sort of think about it like a test because we're used to saying test. So for the p-series test, if you will. In our table of easy, hard, weak, powerful, p-series, easy or hard?
Easy.
Super easy. Weak or powerful? Well,
Super weak.
super weak because it only works on this very specific type of thing, right? It has to look exactly like this. And so it's very much falling in the weak, easy category. When we pick this up tomorrow, we're going to talk about the comparison tests, and the comparison tests take advantage of this really easy p-series and make it much, much more powerful. And so tomorrow we'll see how to take some of these weak things and get more bang for our buck, so to speak. I think there's just one other bit to talk about in this section. Let's see. Wait, I gotta find the right set of notes. Got it. Here they are. Okay. I guess two things. One, let's just update our list one more time. So the list, we have geometric series, we have the harmonic series, telescoping series, the integral test, test for divergence, and now we have that the p-series converges for p greater than 1. And again, what is that p short for? It's telling us about the power, like the power of the series, of the exponent, p or x for power or exponent. So it converges for p bigger than 1. So the last little bit is actually a big deal for those of you that actually want to use this to build things. So maybe you find out that a series converges, like the one that we were working with. So you've got that example where we had the 6 over x over n to the 5th, and you say, great, I know that this converges, but that doesn't help me build a bridge. That doesn't help me keep my airplane in the air. At the end of the day, I need to know what number is this equal to. And so if you wanted to make this equal to a number, you might say, well, what I could do is I could add up the first, I don't know, 50 terms here. So I could add up 50 terms, or I could add up 500 terms, or I could add up 5,000 terms. And what I hope is I might not get the exact number, but I could get the number with a small error. I get a small error. And, you know, if you're building a bridge and your error is, you know, 0.000001, like, small enough error for most of the stuff, you know, the bridge is going to work. If you're trying to put a rocket on the moon, you might need to be more precise. And so the application that you're working on will dictate what kind of error is acceptable, and the error that's acceptable will dictate how many terms you need in your partial sum in order to approximate the actual value. And so what this last item does is it says we can actually use we can use an integral to approximate the remainder. And the remainder, if you will, is like the max error. And so we're saying that our max error would be less than this improper integral. If you happen to be able to calculate that integral, then that would tell you could basically find n. Let me say that again. The unknown is n. So you're always here, you're trying to solve for n. So there's definitely examples in the book. If you work through this particular example, you'll see that you need to have n bigger than 1,000 in order to guarantee that the partial sum is within 0.001 of the actual answer. So this chunk that we've just been talking about here talks about how you could actually evaluate or estimate an infinite sum. Estimate the number, and which kind of series work. There's only one kind of series that reaches a number. For what kind of series converge, or I just gave it away. What kind of series are we working with here? For a convergent series. Wow. Okay. So we can estimate the number for a convergent series by taking advantage of this remainder theorem and the integral test. Again, it's ugly. I think in section maybe 10.6, we will learn about a method using the alternating series that's much easier than this. But this is our first error bounding method. Any questions about this? We're good to go for today. Very good. So may all the techniques that you try today be both powerful and easy. And may you have perseverance when you come across things that are both hard and also strong and powerful. And may you avoid those things that are both hard and weak. Have a wonderful day, everyone. I'll hang on the line if you have any questions, but I'll see you all tomorrow. Take care.
Thanks,
Hey,
Dusty. See you tomorrow.
Thanks, everybody.
Hey, Dusty.
Hey.
What's the class code?
Oh, for the MyLab stuff?
Yeah.
I
I tried looking on your website and I couldn't find it.
think it's in the email that I sent you.
You sent me I think that's the code for the the promo code or whatever for using it
For
for
My Labs?
free. It does. It's not the actual
Oh, okay.
class code.
I'm tracking with you. Do you have a class right after this, Croy?
No, I
right?
like an hour.
Okay, let me see if other people have short questions because I'm just gonna have to look that up.
Okay, you just email it to me and I can sort it out.
Let me see if I can find it quickly. Let's see. Come on. Oh, this is the code. So you're okay. So you got to add back into the class. Is that right? You got to somehow find it. I think it's. You ready?
Yep.
I think it's Wilson, WILSON 41568. 41568. So Wilson 41568.
Yeah, it looks
No
like
caps.
that's right.
Does that look right?
Yeah, it looks like a correct code.
Cool.
Thank you.
No problem. Give me a holler if that doesn't work or you run into issues.
All right. Thank you.
No problem. Khalid, Joseph, questions?